All right, I'm recording Klifto. Don't say
Okay.
anything too crazy.
Uh, Unrecord. Okay. All right. So let's see if this
Here,
will
let
work.
me introduce you real quick, just for formality's sakes. Many of you have been on this already. Chris Klifto, as you know, is one of our colleagues and leaders at Duke. He, similar to Gottschalk and I, has a sort of shoulder to fingertip practice. He has really innovated a lot of aspects of upper extremity. And one of the really cool things he's been really delving into is AI, and that's what he's going to talk to us tonight. So we're really lucky to learn from one of the true pioneers at this point in AI, and as everybody's trying to figure out its role and how it's going to influence our lives in the future. I think it's cool to see somebody like Clifto really take this by the horns, and it'll be interesting to see both learn from him today and see what he does in the future with it. So thanks,
Yes.
Clifto.
Yeah, thanks, man. So as Kara will tell you, I'm like a real cerebral savant and giant. So listen, I just been teaching myself AI kind of around here. A lot of the research projects we were doing kind of started 2 or 3 years ago. But this is like a big overview type, because if you ask me to go to the nitty-gritty details of actually how to program and code, I can't do it. But as orthopedics and researchers, you don't have to actually know how to do that. You just have to have the basic concepts. And then there are plenty of people out there who do know how to do that for you, and it's an awesome thing to learn. So again, this is a big overview of kind of what AI is and what I've learned in my journey over the last like 2 or 3 years. Big thank you to Eric Wagner. Yeah, I don't even know if I have to really say anything, but thank you. Great picture. Um, were you on Accutane at that point? All right, anyway. So this is if you guys want to actually get started and actually go back, and this is a really nice webinar that the Academy put on, and Shane, Noah, and Kyle out of HSS have been doing a lot of great work, at least as far as the education side goes. So go back and watch this. It's really good. It's a good way to get a good overview of what AI is. But the real question is, and I think everyone wants to know this. In fact, I gave these grand rounds at Rush maybe like 3 weeks ago. And this is how I pose it, right? How close are we to singularity? And for those of you who don't know what singularity is, it's a hypothetical future point in time at which technological growth becomes uncontrollable and irreversible, resulting in the unforeseeable changes to human civilization. And that's what everyone's debating is like, are we going to get there? And more importantly, when are we going to get there? I gave this whole presentation at Rush, and Garagos and actually Nicholson at the end just raised their hand. They're like, when are the robots taking over? I'm like, oh, good. I'm glad you guys listened to anything I said. But so anyway, so the answer is I don't think we're very close at all. And this is my buddy's hairline that I wanted to make a joke at Rush. But anyway, so I'm going to give a big overview of what we're doing. And it's going to be the definitions and how we learn to evaluate the models, the orthopedic applications. I'm going to talk a little bit about OpenAI, which is ChatGPT, and talk about some limitations and future directions about where we're going with it. So that's the overall big picture. So if we talk about what AI is, AI was first conceptualized in the 40s by a mathematician named Alan Turing. And I think you all know him. The movie was just made. I think it was called The Unbreakable Code or whatever it was. But he essentially led an M16 team that cracked the Unbreakable Code to the German Enigma coding machine. And that's essentially how they credited that we won World War II by being able to decode their systems. So he had then subsequently created a test for machines' apparent intelligence, which was the first time that machines really interacted with humans. And then he also developed the first automated computing engine, which is one of our first self-storing computers. And this guy was a total savant. He was in the 40s. He actually died when he was 41 of an accidental cyanide poisoning. And it was actually a real sad story. He was rumored to be homosexual, and there was a lot of things that happened with that. And he was chemically castrated. And it's a super interesting story, but we lost one of the true revolutionary thinkers of our generation or any generation based on some unfortunate closed-minded circumstances. But he's essentially the father of AI. And then that continued with this guy named Arthur Samuel, and he coined the term machine learning. He actually developed for IBM the first self-playing checkered program. And it was the first time that a program was actually to self-learn how you played and actually play against you, which was a really cool little bit of history. And then this continued in the 1950s. where a group of scientists got together in Dartmouth, and they were going to make the first AI machine computer. And essentially all they could come up with after years of being together was a calculator. So we weren't progressing as much as we would like, but where did they go wrong? And the question is, it's all related to hardware. No matter how smart these people were and how advanced thinking they were, they could not overcome the hardware issues. And that's where a lot of our limitations are right now. They just didn't have the capability to process quick enough. And the truth is, we also don't understand how like humans reason well, to be honest with you, as much as we think we do. So it's really hard to make a computer system that reasons as well as a human if we don't know how we reason ourselves. And this led to something called the first AI winter. So AI winters, that's going to be a term. A lot of the stuff I'm going to talk about today is just kind of understand the lingo. So the first AI winters refer to some roadblock that happens in AI development that causes it to completely cease in the way that we actually progress, and everyone to stop actually innovating. And that happened after this whole 1950s fiasco. So in the 1970s, the first expert system was developed. And essentially, this was an AI program that was used to reduce the number of computational requirements posed by early computers. And we know this pretty well. There's something called if-then statements, and it's a type of algorithm that was programmed. And essentially, it's spell check. So believe it or not, spell check was a pretty innovative form of AI that was created in the 1970s. So, this continued to Moore's law, and there's like a lot of variations of Moore's law, and anyone who knows AI may have a different definition, but essentially it's a highly quoted law that started in 1965 with Gordon Moore. He was one of the co-founders of Intel Semiconductors, and he wrote this article called Cramming More Components onto Integrated Circuits. And essentially he came up with the idea that if they were able to increase their processors and their integrated circuits, that innovation would double over the next
a little bit.
Oops, sorry. All right, anyway. Innovation would develop over double every year for the next decade. So then they developed transistors. Transistors were initially what dominated electronics, but that went to integrated circuits. And if you see on the graph on the bottom right, that actually doubled almost every year and actually continues to double based on the number of integrated circuits and the potential circuits that they have. Now, the interesting thing was some people say that Moore's law was actually a law saying that technology could only advance for about 10 years and then it plateaus. So you'll sometimes hear that quoted, but usually it's mainly just showing that if you can increase the number of circuits, you can increase innovation. That's essentially what AI is. So when you're talking about AI, there's a predictable type of workflow. It's input of data, and then you develop the model, and then you get an output of prediction. And most of the AI technologies we have now are actually prediction models. And standard regression is only different from machine learning and how it's analyzed. And believe it or not, still to this day, if you're doing stats or data progression, then linear regression outperforms machine learning most of the time. I'm going to get my dog out of here real quick. Sorry, the grocery delivery was just dropped by. Okay, so what is machine learning? Well, machine learning is interesting, right? So artificial intelligence is broad strokes defined as software that can solve problems by itself. And machine learning is a subset of artificial intelligence. And essentially is that algorithms, it's defined by algorithms that can learn from data. So you hear artificial intelligence and machine learning. Well, just think of artificial intelligence as the broad strokes terminology, and machine learning is a subset of algorithms that learn from data. And that's the big difference when you hear the different definitions. So just quickly defining machine learning, it's a field of study that gives computers the ability to make predictions without the need to explicitly program them to do so. Again, this was defined by Arthur Samuel in 1959. I'm going to give a lot of examples to try and explain this. So this is one of the examples of what that means. So a computer program is said to learn from experience E with respect to task T and performance measure P. So if performance on P on task T improves the experience, then you get E. So what does that mean? All right. So I'm going to give you an example. So that means that machines learn to explore and construct the study of algorithms and they can make predictions based on the data. So here's an example of what that means, right? Example, a computer program that tries to block spam. So the task that they're learning is blocking spam. The experience would be you, the user, manually clicking the emails, labeling it spam as not. So it's learning based on the experience, which is you. And then the performance would be the fraction of future emails that are correctly labeled as spam versus not spam. So that's essentially what that last algorithm meant. And then when you break it down, this is essentially it is. It's tasks with experiences and performances. And that's the basics of AI. And this last statement is what is the most important thing about AI is that as the amount of experience increases, and that's data, it's all about data. The more data you have, data is king, the better the performance will be of your AI algorithm. So if you're all trying to figure out how to build your AI models and how to do it, the first step, data, data, data. The bigger data sets you have, the more accurate your AI algorithms will be. So the problem with machine learning and where we are today is that it doesn't have a concrete agreed upon definition, and that makes it challenging. And as we all know, people quote it all the time, and it's essentially just a buzzword for statistics. And distinction is really tough to figure out and to understand how to use it. But if you kind of look at it, this is kind of the big overarching theme of what machine learning is. And this is a cheat sheet. And you can see it could be anything from logistic regression, which we all know because we've all done research in statistics, all the way to neural networks, which is a highly sophisticated type of machine learning, which I'll talk about in a little bit. So, you're going to hear about this a lot. So now we're in the machine learning realm of definitions. There's something called supervised versus unsupervised learning. And if you haven't, you'll hear about this all the time. But essentially, supervised learning is based on classifications. And you can see that on the left side. So classifying things. Unsupervised learning is based on clustering, making these groups and learning from the clusters. And I'll explain that moving forward. But in unsupervised learning, you're given a data set that has no labels. Now, I'm going to give you an example of this, so hopefully it makes more sense. The data is not known, but the outcome of interest is known, right? So let's just say this is an example of an unsupervised learning model. So in cluster 1, you can see there's no arthritis. We'll just say that's on the left. In cluster 2, there's arthritis. So what your algorithm does is the computer learns to pattern recognition between the two clusters. Arthritis versus no arthritis will lead to something called the black box phenomena. And the black box phenomena, as far as I understand, is what all these unsupervised learning models are trying to get to the point where the computer eventually recognizes arthritis like is on the right side of that radiograph, but then maybe you could recognize some more subtle arthritis, which may be on the left side, even to a point where humans can't perceive it. And this is where these models outshine human intelligence. The problem with unsupervised learning is that it takes a ton of data. Like the data requirements for unsupervised learning to detect these different nuances are just ridiculously high, and we'll talk about that in a little bit. And then you have supervised learning, right? So this is a little bit different. So instead of not feeding the program the right answer, like the unsupervised, the supervised tells the computer what the right answer is. And they could be classification problems or regression problems. We all know this, but regression problems are output of continuous variables, they're housing prices, and classifications are discrete variables, which is spam or not spam. But again, in the supervised learning model, it's trained on the right answer. And the beautiful thing about the supervised learning models, and this is why most of them are this, is that the amount of data that you need is way, way less. So for instance, if we're talking about fracture detection, which is what a lot of these models are right now, if you draw the box around the fracture and tell the model that this is what a fracture is, it's going to take way less data to actually train the model on that. The limitations are greater, but it's easier to make. So those are like so you're going to hear about supervised and unsupervised learning all the time moving forward. That's essentially what that means. So when you go to deep learning, that's like the next level of what machine learning is. So if we talk about AI or machine learning as a subset if machine learning is a subset of AI, deep learning is a subset of machine learning. So essentially what that is it's capable of unsupervised learning from unstructured and unlabeled input from variables of low relevance to prediction of interest. And again, I'm going to go over an example because that's just kind of like a tough definition to understand. But it's modeled after the brain's neural networks. And this is something that you're all going to see called artificial neural networks. And these are, again, buzzwords that you'll hear all the time moving forward. They'll be in your research projects. If you could just kind of understand what these mean, then you'll be able to understand and actually do it yourself eventually. So what is not deep learning? Well, it's essentially if you have to manually extract features and then feed them into a model. So for this example, right, you take these photos, these radiographs, and you say, well, the input's sclerosis, joint space narrowing, osteophytes, and that gives you a KL prediction score, right? That is not deep learning. You are telling the algorithm, the model, exactly what's there, and you're trying to get to learn based on that. And examples of that are linear regression, logistic regression, decision trees, and all the other ones that we know, random forests, but we'll talk about them in a little bit. So what is deep learning? So let's just say you took away those characteristics of the radiographs. You took these pixels from the radiographs and you developed a KL score based on that. And again, this is an example of neural networks and recurrent neural networks, and I'm going to give you an example of what those are. So what can deep learning learn? And this is why it's really exciting. Essentially anything. You could train deep learning on images, and that's where a lot of it is getting its traction, at least in orthopedics. But it could be text, speech, EMR, and they're essentially based on our neural networks of our own brain, right? So they're classification systems, which include logistic regression, log loss, but they also can include regression and linear analysis and things that kind of can create space and loss of function, which is really interesting. So how does it work, right? So they're essentially artificial neural networks, and artificial neural networks have discrete layers and connections to other nodes. So they're complex layering that mimic our brain, and they give the network and the algorithms the ability to learn and make more complex and subtle patterns. So this is kind of, this is an example, and I hope this makes sense. This is just a big overarching illustration of what a neural network is. So I'm going to go really slow, right? So your first layer on the left is your input layer, right? And that's your biggest nodes. Oh, here we go. Yeah, sorry, it skipped a few. So this is something called the MINST database. And this is kind of how neural networks are trained, but it's a really good way to kind of explain them. So the goal of these programs, and for this specific model, is to take a handwritten number, in this case, it's the number 3, and then figure out a way for this neural network to tell you what is the prediction of just putting in a number 3 that you hand wrote into actually predicting the 3 correctly. So how do these neural networks work? Well, the first thing they do is you take these pixels, right? And they break them up to 28 by 28 grid pixels. They unravel them. So 28 times 28 is 784 for Eric. You know, just trying to get that there out there for you. And that makes those pixels into this big train. And then those pixel trains of 784 neurons is put into the neural network into a one-dimensional train of data. So that goes into layer 2. So layer 2 is something called the hidden layer. And this is where most of the computations are performed, in this hidden layer. And this is where all the science goes. The hidden layers are reformed to the black box, which is limited to insights and features. But essentially, this is where everything happens. It essentially creates higher level of computational algorithms that will give us the highest probability of getting the number 3 that we unraveled into these pixels, to say that all number 3 is getting put into the system would actually be the correct number 3 prediction. And the cool thing about these neural networks is if the probability, they have these things called activation energies, right? And if these activation energies, which is a threshold of probability that the correct pixels rolling through to get that number 3, if it's not correct, it boots it back into the earlier hidden layers and does increased probability algorithms to try and get to a higher prediction factor until it kicks it all the way on the right. It's just super cool stuff and really innovative. So the problem is that deep learning isn't always linear, and normal logistic regressions have trouble predicting things that have 2 values, right? So the question is like infection prediction, right? And the example I like to use is BMI, right? So BMI, if your BMI is too low, you have a high risk of infection. And if your BMI is too high, you have a high risk of infection. So this is where deep learning actually excels, when there's non-linear outcomes. And this is where it's being used in orthopedics for the most part. But natural language processing is something that we're kind of working on right now. And this is the process of how computers understand and interpret human language, with the goal of generating structured information from unstructured free text. So the data isn't entered, but an algorithm extracts it. And I'm going to give you an example of what that means, right? So let's just say that you have that same patient with NEOA. And this is really cool. Like, a lot of stuff is coming out of this, but essentially the note is populated before you even see the patient from the primary care notes and the PT notes about the patient. And this is all through AI. Then the same AI algorithm analyzes the medical records to say, has the patient been optimized? Have they seen their medical doctors? Have they done the things to actually get insurance approval? And then it actually goes through the images from the radiology reads, confirms the diagnosis of OA, and then sends that to the insurance company for authorization to see if they be pre-approved before you even see the patient. And this is called natural language processing, essentially a process where it's taking free text, extracting all the important information, doing the next steps for you, and then before you even see the patient, they're totally optimized. It's awesome. It's going to change how we do things. So the question is, how do we evaluate a model? Well, there's a couple ways to do it, and we all know the confusion matrix. I'm not going to talk about that. It's just the internal validity, which includes accuracy, sensitivity, precision, specificity. But if you're going to know anything, it's the receiver operator curve. And I'm not going to teach you statistics. I mean, you all know it. You probably know it better than I do. But when you're looking at these different models, especially when we're seeing in orthopedic literature, you always want to look at the AUC. And the area under the receiver operator curve is the AUC. And it's a really good way, from broad strokes, to understand how good the model is performing and how accurate it is. So this is just kind of what an AUC means, right? So if you have a 0.5 AUC, that essentially says that the model isn't any better than 50% chance. If your AUC is in between 0.7 or 0.8, then that's a pretty good model. It's not the greatest. So if you're reviewing a paper, you're reading a paper, or develop your own models, you see 0.7, think of it like, it's okay model. But it's not great. And then as you get closer to 1, it goes to outstanding. If you ever see a model of 1, I mean, that's just through the charts good, and it's almost impossible to get. So how do you evaluate a model? Well, one is the internal validity, like we just talked about, looking at the AUC number, and then also looking at the different confusion matrix numbers that we all know. But the second one is external validity. So if you see a really good working model, it's usually a model that has taken its data set that it was created on, and then has subsequently got another data set and validated all of its results from a different cohort to make sure that you're actually doing something correctly. So there are a bunch of different common areas for implementation. They usually involve risk stratification, clinical prediction models, and image analysis, which I'll go over as we get to the end of this presentation. We actually get into what we've done and where orthopedics is right now with AI. So this was our first attempt at AI. And this was the Duke Rush Shoulder Consortium. And essentially, it was a 2-institution system where we took 5,000 shoulder arthroplasties, and this included anatomics and reverses over the course of essentially 20 years. And the reason why this worked out pretty well was because Duke is probably similar to Emory. We take everyone, we have very sick patients, and then Rush is kind of just the opposite. They have only essentially private payers who are very well optimized. So we built the model in 2 very distinct different groups. And we used statistical analysis, which included multivariate logistic regression. And then we validated that within that, analyzing our models by the area under the receiver operator curve. And then we combined this with deep learning, machine learning models. So we decided to figure out what was most important to value-based care. And that was largely because, and we could do this at Emory too, you could generate huge data sets through Epic from a code we generated here at Duke, which essentially generates everything you can see on the right. 9-day readmissions to Alex-Haller comorbidities. All this data was generated by a code that we developed here. And we looked at outpatient appropriateness. Why is that important? Well, it's cost savings relative to inpatient admissions. 9-day readmissions, that's penalized by CMS. Discharge to SNF, which was a primary driver for excess total cost, which we found. And extended inpatient length of stay, which is considered to be an adverse event by itself. And we did, I thought we did some pretty cool stuff. We did a risk prediction tool for 9-day readmissions. And this was Grant. He did that one first. And then we validated the risk prediction tool, which is a great way to show that your models work well. And we did that in 2021. And then we did a validated preoperative risk prediction tool for extended length of stay. And these are all publicly available, actually, through the Duke website to be able to see which of your patients are appropriate for all these characteristics. And, we did okay. If you go back, like our AUC was 0.87, 0.72, 0.8, which is not bad, but we really wanted to understand what outpatient appropriateness was because we thought that was most clinically significant. So we looked at this study, and Eric and Mike, if you're on this, you'll love this. So we did the study on the short stay after shoulder arthroplasty, and does that affect readmissions with Medicare? And it actually got totally rejected our first time around. And Nicholson emailed Malin and said, this is crap. And then lo and behold, it got rebooted into the system, and it was the JSES editor's pick for best article of 2022. So that just goes to show you, if your articles are getting rejected right off the bat, it actually may be a good article. And maybe if you believe in it, you should go to the editor and say, hey, this isn't right. And then so we also then looked at appropriate patient selection for outpatient shoulder arthroplasty as a risk prediction tool. Again, same models. We thought we developed this awesome tool. And then essentially the Murthy group just published their results validating their own into our algorithm. And they said it was total crap. They said our model performed highly inaccurately. So it just goes to show you that maybe what we're doing isn't that great. And then again, the AUC was 0.76, which kind of goes to show it's a good model, but it's not a great model. And Murthy actually found that. So our second attempt at predictive modeling was to hit bombs. So I'm a golfer. I like golfing, and I want to get into sports prediction. So we developed a huge data set looking at club head speed. So for any of you who are golfers, if you're 43 years old, you're over the hill. You're going to start decreasing your swing speed pretty quickly. And this was just a regression that we did to find that. But we developed this out tree algorithm to figure out how do you hit deeper shots, longer shots. And essentially what we did was we went back and looked at this tree algorithm where we took swing speed and we took different performance metrics like bench press, squat, counterforce jump, range of motion, lat pull down, to see if any of these things mattered. And we developed this tree matrix, which essentially was a shade analysis, which essentially grouped you into different things. So for instance, this was me actually being put into the algorithm. I'm in these yellow squares. So if you're talking about my example, I had to throw a medicine ball as far as I can throw, that was 4 pounds. And that put me into node 5. So when I got put into node 5, the algorithm ran and said, okay, you're at the end of this node, you're at this performance. The next step is going to be for you to do a counter movement jump. So then it had me do a counter movement jump, which was on the right. And that caused me to be kicked out and said, your swing speed is X, based on just those two exercises. Now, if you had a different chest pass, it would put you into node 9, which would have you do more different type of exercises to get you to the probability where it felt that the algorithm could produce your swing speed accurately. And as soon as it does that, it kicks you out. And that's essentially what a tree algorithm is, which was a lot of fun. And that was a chain analysis. So, there's a lot of cool stuff going out there right now. This was Kyle Kunze, I think I said that right, and Shane No. They've been doing a lot of work on machine learning, and this was just a cool study. This was one of the first machine learning studies that I've seen. It was a systematic review, just looking at different machine learning algorithms to see if they can predict minimal clinical differences. And essentially what they found was that machine learning models could do it well, but there was only one externally validated model that performed well. And they said that it does have the ability to discriminate, but it's only based on certain outcomes. So it's interesting. So then if you moved on to like more of what we care about, which is image analysis, this is a study looking at the artificial intelligence and can they analyze trauma radiographs? They trained 256,000 wrist, hand, and ankle radiographs. And this was a model that they coined as openly available deep neural network. So that was that complex neural network that I was showing before. And they essentially found that there was only a 90% accuracy of even just developing laterality, body part. And when it got to fractures, it was only 83% accurate. And they actually concluded that it was not better than your typical radiologists. So did we get any better? This was a cool study in 2020, essentially looking at, are we able to actually detect fractures that are occult scaphoids? And they use this neural network to figure out, are they able to do it? And they concluded that they couldn't, right? They found that deep learning algorithms had trouble developing or detecting scaphoid fractures that were obvious to humans. They had a lot of false positives, but we got better, right? So this was a study that they repeated in 2021, increasing the number of data points. So like when you increase the number of data points, your neural networks get better. And they actually concluded that they were just as good as radiologists, which honestly, like if you think about like, how is machine learning probably going to get into orthopedics, not orthopedics, but just medicine? It probably is radiology. There's going to be a lot of fracture detection. There's a lot of neural networks out there that have been doing really well based on fracture detection. And, this was another really good one that looked at x-rays. And this was an image analysis where they essentially developed an algorithm looking at 5,000 and 5,204 pelvic x-rays. And their model for detecting fractions was through the roof. It just did really, really well. So this was a study that I hate more than any other study out there. And I don't know if you saw this, Eric and Mike, but this is Larry Galata's study that came out, I think in May in JSCS, where they took 3,000 implants from TSAs and RTSAs. They did a deep learning algorithm, which trained 22 different implants to see if it was able to predict the implant that was unidentified by someone who was unfamiliar with it. They found an amazingly quick classifier. It took them 0.79 seconds to find the actual implant. And the accuracy was 97.1%, which was really great. Why do I hate this? Because I have spent the last year of my life developing this implant database for ASCS, and it seems like it's going to be a total waste of time because things are being developed. Anyway, this is coming out next week if anyone wants to see it. But, time wasted, I guess. So then we get to generative AI. So generative AI is really, really cool. And like, this is where we start getting to the point where like, this could be anything, right? So this was an awesome study where they took 250 million pelvis x-rays, which is just like crazy amount of time putting into it. And they were able to produce unique x-rays that were totally indistinguishable from actual patients and radiologists and orthopedic surgeons. It's crazy. So that image on your right is something that I generated, and it was totally indistinguishable. They have bowel gas, they have everything. And when we start thinking about where AI is going, it's probably this generative AI, to be honest with you. And then we all know ChatGPT. So ChatGPT is super interesting. It's a form of generative AI, and this is an OpenAI that we've all heard about. And again, it's that natural language processing, which we talked about a little bit earlier. But the crazy thing about ChatGPT is, you think it just came about. They had to train 1 trillion parameters, 1 trillion at an estimated cost of over $100 million to get where we are now. And it is going to change the world. But man, that was a big undertaking. The thing about ChatGPT right now is it just forms narratives and language. But there's going to be a point really where it generates different type of algorithms. And, this is a little tangential, but I don't know if you all heard about this, but Facebook actually had a form of generative AI in like a ChatGPT type of segment. And they actually had to shut down the entire program because the program started developing its own language, which they couldn't decipher, and started coding itself. And it totally went out of control. So they had to take down the entire program because they actually had no idea what was happening. So this is kind of like a world we're getting in, and we'll see what happens. So this is kind of stuff we're working on right now. We decided to go into the machine learning section of image analysis. And one of the things that anyone who does a lot of shoulder arthroplasty, the bane of their existence is actually acromion stress fracture. So we're trying to develop an AI model to look at different type of radiographic parameters to say what's going to cause a acromion stress fracture or not. And then we actually just finished our data yesterday. And if you lateralize over 2.75 millimeters from the center of rotation of the humeral head, you'll almost have a 5-fold increase of developing a acromion stress fracture, which is a really cool finding that we're going to be publishing soon, hopefully. But that was all developed from our AI algorithms and looking at countless different types of radiographs and taking the measurements that we all know, which was a lot of fun. There are a lot of different computer vision programs out there, and this is kind of like beyond the scope to talk about it, but there's something called phenotyping. Like, can you say like, what type of classification of a total knee arthroplasty you have, like who will do well from a total knee. The stuff on the top left is this new thing that we're doing, which is a segmentation type of algorithm. We're essentially looking to see glenoid morphology for instability, looking at glenoids as a 3D structure and not just that 2D image that we're looking at, to see if slope has anything to do with recurrent instability. Is it just bone loss? And there are different type of networks that you can do for that, which has been a lot of fun. Hopefully we're developing some good stuff. I hope this plays. This is something called the deep fake. This is the scariest thing that I've seen. I'll see if I can replace that. But here you go. So this is just some rando person there doing a head structure and essentially recreated Obama here perfectly. The scariest thing about these deep fakes is that there is no way at this point, apparently, for like intelligence agencies to actually distinguish between deep fakes and humans on the best models. And sadly, like it was developed from nefarious purposes. It was actually developed by the pornography industry for really, really sick purposes. But this is where AI gets really scary, when it gets into that sort of world of just kind of pure evil. So if you're going to develop your own AI, like I said, the first thing you have to do is figure out a task. Like if you're going to do your own one, that is repetitive, automatic. And if they can solve it, then it'll take time away from other important things you can do. And the best ones that are the ones that can bucket things into categories. For instance, fracture or not fracture, acromion fracture or not fracture, distalization, lateralization, all things that you could bucket. Those are things that AI can predict. And then you have to ask, like, does your organization actually collect the data to be able to do it? And most of the last 2 or 3 years, Kier excluded because he hasn't done any research for me, which is fine. But the rest of us have been trying to figure out how do we actually get all that data to make these models. And this is just something you do like fracture detection, which is, is this a distal raised fracture, which is easy to do. The biggest takeaways is that machine learning is a branch of artificial intelligence, which explores the construction of algorithms. It has numerous applications within orthopedics. And then once you understand the different nuances between what machine learning is and what the different definitions are, then you can actually make your own type of algorithms. And the potential is limitless, especially in orthopedics. And we're just getting to the frontier of that. And these are my references. So thanks for having me. And by the way, I'm joking around. Like, Kier does a ton of research. I just had to poke him at some point in this presentation. So, any questions?
Hey, it's Joe, one of the fellows. So that was super interesting. Thanks for going into that. I've got a technical question.
Yeah.
Who writes the code for this stuff? Like, let's say I'm an academic surgeon and I want to develop a machine learning algorithm to look at whatever. I imagine this is requires someone who's pretty skilled at writing these programs, right? How do you approach that?
Yeah, so I mean, you guys will have this at Emory if you're interested in it. What we did at Duke is there's like a whole AI division here. But you would be surprised. Like, I'm actually teaching myself how to code now, and it's really not that. I mean, a lot of the programs out there, like, SAS has programs how to do it for you. There's a lot of commercially available things. It's just what you have to do is you have to. My biggest takeaway for how to do that is learn the different types of algorithm languages, right? There's different types of ones, like I was talking about, like the natural processing, there's Bayesian, there's all these different types of AI. Once you learn that, you can actually go to like SAS and they could actually do it for you, or you could have one of your programmers at Emory kind of do it for you in the AI division. And it's not hard to do. The hardest thing is collect the data, have the idea, and then the rest kind of works itself out. If you want to teach yourself, there's something called Coursera. I don't know if you ever heard of that. And there's a really good AI program from a guy from Stanford who teaches you how to do it. And I just read books. Like, you're all smart people. Like, it's not that hard if you have a mathematical background, to do it. Most places actually have masters, and we're currently trying to enroll in an AI master's program here to see if they will let us kind of audit it just to get better at it. But that's the beautiful things of being at Emory, is you actually have like limitless resources, and you don't have to know how to do it. You just have to, if you could understand the broad strokes of AI and what it is, then you could find someone to do it for you.
Sure. That makes sense. Thank you.
That's interesting, Klifto. We literally part of the Codman Society. It's like this avant-garde, part of like this JP's part of the stuff, and he's got a group of I don't know how many people. Eric got us involved. But we literally just have like the same study that you guys did, using two different models essentially, using Medicare claims database and doing the same thing, predictive adverse outcomes after essentially outpatient shoulders to see who should be getting them and who shouldn't. But instead of 5,000, right, it's got, I don't know, 50 or 60 or even more thousand shoulders over however many. But the problem is you're at the mercy of what data points you have in. So, you know, they took essentially 16, the AUC is about 0.7, so it's okay. But, you know, part of the problem is it's how good are your variables going in, and the number of, not just the data points, but essentially the number of patients or whatever that you can actually put in addition to the variables, right?
Yeah, I mean, I think I read that paper. Is that the one you submitted?
No, we haven't. I'm literally submitting it as we speak.
Yeah. Okay. The problem with, so I've reviewed a lot of papers. They had me review for JSES for this because I know it. So most of the machine learning ones, the problem with the large database ones is the data is so imperfect, and to actually get these models to work really well, you have to have pretty pure data. And that's what we spent the most of our time doing with our data set, was to make it as clean as possible. And then you have to also you also have to figure out what your model is, right? There's something called a lasso technique where you can essentially kick back.
We use both. We use that, and then we use the other one. So we did both of them. So we have that technique, and then we did essentially the 80-20, which is essentially, you know, you take your data set, use 80%, use the other 20% to validate it. I mean, I think ultimately the problem though is, yet again, like 5,000 joints is still nothing, right? When we started looking at some of these things, we're like, oh yeah, we want tens of thousands to run the model. That's part of the problem. Like the quantity that you have for stuff that we do is relatively like so small because you have small centers. And then the moment you have, one of the things that we talked about that the whole reason I went to Australia was they want to do what they call federated learning. I don't know if you've ever heard of that or not, but essentially you take data sets from a lot of different institutions, it feeds into a central computer and then spits stuff out separately so that the algorithm keeps changing, but then you have your own network, essentially algorithm, and then you have a combined one and it starts to see which one's better and which one's worse. It's very interesting.
Yeah. What's it called?
That's one of the more advanced AI techniques, but to do what they call federated learning, where they essentially have models where you have inputs coming from multiple places, because theoretically, and that's de-identified data that they are sharing, which is crazy. That's how they want to get around this, that you can de-identify the data, share it, it comes back, and then you can technically run models on it. But it's super hard. The UK is probably the farthest on this because they've got access to all the like genetic genome stuff things that they're doing. It's insane. It's crazy. It really is.
Yeah, it's cool stuff. It's fun.
I don't know if anyone else has any of the other stuff. Any questions? My question, so let me ask you this, Chris. Have you actually implemented any of these questionnaires in your own clinic? Are you asking 16 questions to your patients now?
No, the problem is, like, you know, when we boiled down like that even those predictive models that we generated with, we found that there was just a couple things that were really important. And then once you know, that's just, do you have renal disease? What's your social situation like? It's kind of like, okay, then what's the point? Especially because now, I mean, I don't know what your guys' practice is, but like 95% of my patients are outpatients at this point, just based on those two parameters. And my kickback rate has been really low. So a lot has changed. And believe it or not, like COVID has actually made things a little bit more difficult because the models that we generated before aren't applying to the ones that are happening now, right? That was all like 2019 data. So
sure, no, it's old, right? It's old. No, you're 100% correct. And now, prior to that, they weren't doing as many outpatients, right? We actually, Eric, myself, and we wrote a paper on that. The number of outpatient shoulders skyrocketed after COVID, like skyrocketed. And then my argument is, just to say that they have a post-operative outcome that requires readmission doesn't mean that if you do them as an inpatient, you're going to prevent them from being readmitted once you discharge them a day later. I don't know. That was one of my hardest sells is everyone's like, oh, well, that may means you want to put them in the hospital after surgery. I'm like, you're assuming that something that you do in surgery is going to change their ultimate thing 30 days later. It may not. Right? I mean, that doesn't necessarily, in my opinion, it just doesn't necessarily mean. I mean, I'm curious to know what Brent Ponce is on too. I'm curious to think what Brent and then what Wags had to, what you think is, why do you think shoulders went off the CMS inpatient list only to go back on it? I mean, I think I know what the answer is, but I'm curious to see what y'all think.
I could tell you the answer to that when they say theirs. I did a webinar last year on it for AOS. It's very simple, but I'll let them answer first.
Brent, what do you think?
Well, I'm interested in just hearing what the real answer is.
Yeah. So, I mean, do you want me to just tell you what it was? So
yeah, the hospitals needed the money. They lost so much money from the total knees and hips leaving the stuff. They needed the money. I don't know. Unless Klifto, you tell me otherwise.
Yeah, no, it wasn't. It was actually a political thing. So, in the Trump administration, there was, I think it was 20 different type of procedures that were going to come off the inpatient only list and go to outpatient, and that included total shoulders. And there was some C-spine and some genital stuff that included that. And then legitimately, administration changed, and as a political move, the Biden administration nixed all that, said it was too rushed, and they had to evaluate more. And the theory has been that it was just actually a political battle between the two parties, and that's the only reason. There's a lot of validity to that, but it should come off. The problem with it coming off of the inpatient only list is that there's been a precedent that apparently, and maybe I'm wrong here, but once it comes off the inpatient only list, usually the RVU reimbursement goes down per case. So there's been some advocacy to actually not get it off of that for that reason, which is interesting.
Yeah, I mean, look, I think part of it probably per our chief of nursing and everything else, they think it's related because the hospitals lobbied back and they were losing too much money. But I don't know if any of that's true since everything's shifted. But that's a valid point. You're probably right. To some extent, it may have had to do with when and how. But I mean, they reversed course pretty quickly.
Yep. It was almost instantaneous. Like it was like change of administration goes back on.
Awesome. Any other questions for Dr. Klifto? Perfect, Klifto. Well, thanks, man.
Related.
Oh, go ahead,
sorry.
Nicole.
I was going to say, Dr. Klifto, I have a related kind of question. How do you, as someone who's an innovator, who works in the academic space, who's trying to innovate also on the technical side for certain factors that can't be captured by these AI algorithms, how do you balance that with also this very data-driven approach where, you know, potentially some of these things could be leveraged by hospital administrators to have you make certain decisions about how you indicate patients for surgery? Because I feel like that tension is kind of emerging in this conversation that Dr. Gottschalk brought up, but I'm curious, how you kind of work both of those sides of your mind.
That's a good question. I think the best way to answer that is we're pretty far off from developing anything that is good enough or smart enough. Like we are so in the infancy of AI and orthopedics. Like there aren't a ton of studies out there. The ones that are coming out are pretty flawed as we're all trying to learn it. So hospital administrations haven't had that ability yet. But essentially, that's why I think it's important for us to actually be developing this research, right? Because if we're developing the models, we're able to actually say what is clinically important and what's not. I think that's why we all have to be doing this because, like it or not, this is happening, right? And we can either be a part of it and influence it, or we can have someone else do it. And I think that's why it's important for us to all do this type of research. If that's the best way I can answer, if that makes sense.
Yeah, no, that's awesome, man. It'll be really cool and unique to see kind of how it goes. We haven't had as much luck getting our AI people involved at Emory. But as Ketchup mentioned, we've kind of reached out to other organizations and working with them. But yeah, it's really cool stuff. Like it would be interesting to see, especially radiographs, predictions, like telling you how to do shoulder replacements, that type of stuff with all the planning software. It'd be interesting to see where all that goes. So it's really cool stuff, man. Congratulations on all that you've done up to this point, and yeah, that's it's cool stuff. That Epic algorithm's awesome. We'll maybe have to rope you in to teach us how to do it. Maybe we can add some to your data sets.
I mean, I think I told you this before, but as far as I know, we have a DUA with you guys because our group did it with your hip and knee side. And then it's just a program that we could pull for your arthroplasties. It'd be pretty quick.
Yeah, that'd be awesome. We should explore that.
Yep, for sure.
Anyways, Klifto, thank you very much. Anybody else have any questions for him? All right, cool guys. Well, thank you all very much, and I'll post this on the Emery Sherman YouTube. Is that okay, Klifto, to post this on the Emery Sherman YouTube afterwards?
Yeah, totally, absolutely.
Cool. All right, I'm gonna post this for anybody who missed it or wants to go back and review it. A very, very comprehensive review. So thanks, Klifto. Excellent job as usual.
All right, see you guys later. Thank you for having me.